And the stability of equations with second order derivatives is actually a lot worse, because if you plot the lambda of this approximation to second order derivative, all these eigenvalues are purely real. I mean, none of them are imaginary, but they go back very far, right? They go all the way to minus 1 over delta x squared. All right, not just the, I think actually not just the 1 over delta x squared there. I think it's actually minus 4 over delta x squared. Okay, the eigenmode being, if you have a u and x, if the solution is positive, negative, positive, negative, positive, negative, and if you apply this finite difference operator, you actually get minus 4 over delta x squared multiplication. Okay, so that means if you use an explicit time integration scheme, my kappa, okay, times delta t over delta x squared has to be less than order 1 number. Right? Because I need to scale this space of lambda by kappa, which is here, times my delta t, and I need that to fit into the stability region, like one of these circles, maybe minus 2, maybe minus 2.5, minus 3, but not something very large. All right, so if I use explicit solvers for an equation with a strong parabolic term, my time step size is going to be very, very severely constrained by the square of delta x. So now that goes back to now I just said if I have high Reynolds number flow, we use implicit solver. If you, on the other end of the spectrum, if you have low Reynolds number flows, because of this constraint, you also want to use a implicit solver, right? Okay, and only kind of in the intermediate region, when you have a not super high Reynolds number, not super low Reynolds number, explicit time integration schemes becomes pretty popular. All right. Okay. So this is relating to the stability of finite difference schemes. So skip this, and finite difference can be used not only for linear equations, it can also be used on nonlinear equations. So for example, we have been looking at this equation, this linear equation, right? But what if I'm going to switch this constant wave speed to make it a non-constant wave speed? And that's actually the case for many of the practical differential equations we want to solve. For example, in aerodynamics, we are solving for the velocity, right? And the wave speed is actually directly related to velocity. The three wave speeding in the Euler equation or Navier-Stokes equation are the flow velocity plus speed of sound, flow velocity itself, and flow velocity minus speed of sound. So what if we make this wave speed actually equal to the flow solution u? What we get is basically big U equal to small u. What we get is small u times partial u partial x equal to kappa second order derivative. So this becomes a nonlinear equation because if you have two solutions to the same differential equation, here, when BQ is constant, you add these two solutions, the sum of these two solutions, it's still going to be a solution to this PDE, right? Or if you multiply an existing solution by a factor of 2, it still satisfies the PDE, but no longer in this case. If you scale the solution U by a factor of 2, you plug in, this term is actually scaled by a factor of 4. So it's no longer going to be satisfied. We get a nonlinear equation, right? So we lose the property of linear superposition. So, but no matter what, we can still solve this differential equation using finite difference as long as we can approximate this as ui plus 1 minus ui minus 1 over 2 delta x, and we are going to be approximating this by this over delta x squared, right? So, and this term, the whole of this term is just going to be ui times this. So we can just write down the discretized scheme to be that. We have no problem encoding that up into MATLAB and solving it, right? So let's try that. I have a little bit of time. Let's see if I'm fast enough in coding this into MATLAB. Yeah. I mean, the real interesting thing is going to be the behavior of this equation and for different values of kappa. And that motivates us to our next lecture on Wednesday, which is how do we use finite volume scheme to solve equations instead of finite difference. Okay.
Historically, when were these schemes derived? Is this like stuff from like when computers first came about, or does this predate all of that?
It predates all of that. I mean, back in the early days, people just use just the pencil and papers to solve all these equations, and even parallel computing came over like long before there was computers. At that time, parallel computing just means a room full of people. Everybody uses pen and papers and just pass results to the next person.
That sounds horrible.
Actually, like back in World War II, I think that's because people needs to do so many calculations. It's like it's what they call computers, actually a job, the type of person whose job is doing that. Right, there is a very strong shortage of computers in that time, and one of the reasons people actually created the electronic computers is because human computers become so scarce and expensive to hire. They say, okay, what the hell? Let's just let's just make some machines to do the job. Okay. Well, I guess we can code up the solver for this equation in the next lecture. This equation is called the Burgers equation, and this equation is actually one of the primary equations people use to test CFD solvers, because this equation shares so many commonalities with real Euler equation and Navier-Stokes equations that a lot of schemes that worked on this one almost automatically worked for Navier-Stokes equations. All right, so I'll see you on Wednesday. We'll look at why finite difference fails on this equation and what can we do differently to use finite volume to solve this. All right.